So thank you all for coming to my talk. This is a talk on scaling a logging infrastructure. Okay, it's very much centric to a central logging infrastructure, and this talks about the architecture that we had to make and change as we went through, but also the pain points and what we would do differently. My name's Paul Stack. I have some contact details right here. If anybody's interested in talking more about this and you don't want to speak at the end, please get in contact and I'll happily share any code or any snippets, whatever. This talk was actually designed for use at a company called OpenTable. Since I submitted the talk, I no longer work there. So it's only like 2 months ago I left the company, so the talk is very relevant still. We had a lot to do, and we went through some of the busiest times of the year at this talk, or with this login infrastructure. So I'm still in a position where we can still talk about it. I may not mention the name OpenTable. If I do, I may get a slap, but that's okay. I'm a reformed ASP.NET and C# developer. Is there any C# or .NET developers here? Yeah. Oh, it's strange being at a conference and not having lots of .NET developers. Java developers? Lots of Java developers, yeah. I feel about this small. I've just got in the Java world and the JVM world, and it's just blowing my mind. I'm a complete DevOps extremist. I love everything to do with DevOps. I'm a developer who's moved into the operations space, and it's awesome. And I'm a conference junkie. This is my 3rd conference, speaking in 10 days. And I don't even know, I can't even remember, I actually forgot what city I was in last night. So the background to this project was that I was given the task of replacing a legacy logging solution. Okay? Now, there's 2 very weird words in there. Firstly, legacy, because it was a 12-year-old central logging solution that didn't scale. And the other weird one is a logging solution. So the logging solution of the company I used to work at was a SQL Server database, and each application writing their logs via stored procedures. And that was painful. I see some people shaking their head and laughing. People still do that. So we actually, the CTO turned around and said, let's buy a logging solution. So we were going to use Splunk. No offense to anyone using Splunk, but I feel it's extremely expensive, and I felt that I could do just as good a job using free tools. Now, looking back, maybe the trade-off was that Splunk would have done it faster, but we grew organically and we learned a lot as we went through this. The reason we had to change this was because all the logs were in SQL Server. We started having developers writing select statements and not putting no lock on there. And they were locking the database. So developers having access to a database can really not be fun. So we started with what we call iteration 0. And iteration 0 was we took the ELK stack. Okay? ELK is Elasticsearch, Logstash, and Kibana. 3 open source tools that work very well together. They've been created by a company called, they're now maintained by a company called Elastic. And they were all different projects that sort of went very well together that have now actually all gone under the same company. And we had a developer who was like, okay, I can take this and I can deploy it. And they took the single jar file from the website, which had all 3 combined, and deployed it onto a server. And they were like, right, we have a centralized login solution. Let's put some DNS around it and let everybody bombard it. It worked for a while, every day. And it fell over for a long time, every day. And we could approximately take about 15 million messages through it. Okay, so that's not a huge amount. Now, a message to us is when someone hit the website, that would create requests internally, and every one of those requests that came through our system was a message. Okay? And then we had the logs for the errors, and we had people were sending extra messages. So when you think about it, 15 million was not a huge amount. And it proved that we had to do something better. So it was time to make it production ready, and they gave it to my ops team. And it was time to implement some DevOps practices. Buzzword time. And it's quite nice, actually, because all of this was all done via Puppet. And the last talk in here was about testing your infrastructure code using Jenkins, and that was all based on Puppet as well. This is not a Puppet sales pitch, I promise you. So, iteration one. Iteration one was that we decided to split things out. We would have different server types and different clusters and everything together. And we ended up with a solution that looked like this. So ignore the secondary data center right now. Okay, that's something slightly different. Inside the central data center, we had application servers talking to log processors. We had data flowing from log processors via log indexers into Elasticsearch. Okay? What we had effectively done is take the 3-in-1 and made it 3. No longer was it one central server, it was clusters of 3. And we had some fundamental problems here. Inside a log processor, it looked like this. We had an instance of Logstash and an instance of Redis. Anyone use Redis? Has anybody used Redis in clustered mode? Exactly. Nobody knows how it works. It's a myth. And effectively, applications could talk into our log processors in two ways. It could either connect directly to Redis, okay, because some of the application developers, they were .NET application developers and Node.js application developers, were like, well, we can just create a HTTP connection to Redis and throw a message in. Okay? And then some of the more sensible people, like in the ops world, were like, HTTP logging, that's not a great solution. Let's log to Logstash. And then Logstash would forward it into Redis. Effectively here, Redis became our existing queue. It became our persistence store. Redis is not good as a persistence store. Firstly, I take that back. Redis can be a very good persistence store. We didn't understand Redis enough in order to make it effective. So therefore, we turned off the store into disk, and we stored it all in RAM. That was a terrible idea. Terrible, terrible, terrible idea. And I'll talk to you about why that's the case. So let's look at the architecture diagram again. We had a main data center, and then we had lots of secondary data centers that were built exactly the same way. And we were like, how do we get the data from Redis in each of our data centers around the world into our central database, or our central data center? And we were like, let's just throw another instance of Logstash in there. We can read it out of Redis on one side and put it into Redis on the other side. We had multiple problems here, absolutely multiple problems. Because we were working on a push-based system, if there was a connection failure or a network failure between the secondary data center and the primary data center, we would just lose logs. 100%. We had no idea how many we were losing. We had no guarantees to developers that their application logs may actually make it to the central place. They were just like, are they there? And we were like, I don't know, check. But we had a bigger problem. When we had a network problem, and Logstash couldn't communicate with the main data center, Redis was filling, and filling, and filling, and filling, and filling, and filling. And it got to the point where we'd flatlined. So we had some graphs, and we could tell how much RAM was being used on the Redis cluster, and it flatlined. And we thought, okay, so we've reached our saturation point. Yeah, we didn't realize that Redis was dequeuing. So as it was writing on one side, it was dequeuing on the other. And it was flatlining because it couldn't actually grow anymore, and Redis was just dumping all this data. Yeah, not good. And then, when Redis crashed, we lost it all. We lost all the data that was in RAM because we had to restart Redis. There were multiple issues going on here. There really were. The biggest problem that we faced was that we couldn't cluster Redis. Redis can be clustered now, like people can use tools like Sentinel, etc. But it's still a bit of a pain to cluster. It's still really hard to use, and it's really hard to cluster. And I generally wouldn't recommend it. So, we found a tool called Apache Kafka. Anyone know Kafka? Yay! a few people. Only people really on this side and one here. Is this like a split in the camp? Oh, it is? You don't like them? You're not sure? Okay. Maybe at the end, you can tell me why. So for those who don't know, Kafka is a distributed pub sub, and it's designed to be scalable, fast, and durable. Okay? And I took that exact definition, and that was from the Cloudera blog. It was originally created in 2011 out of LinkedIn. Boo, LinkedIn. And in 2014, the engineers that actually built it formed their own company called Cogent. So you know what? That's really annoying. Can I hear myself? Yay, much better. Called Confluent. And it's become a really good pub subsystem. A lot of people are starting to use it. It's got a lot of cases now. It's got a huge amount of use cases around logs, around event sourcing now, and it's got just normal pub sub, etc. And we're going to talk a little bit about Kafka and what it is, okay? So Kafka is made up of 4 things, okay? Topics, producers, consumers, and the simplest part of the lot is brokers, okay? If you can grok what these 4 things are, you're probably going to find Kafka quite easy to work with. So all communication is done via TCP, and it's backed by Zookeeper. Does anybody not like Zookeeper? Zookeeper rocks. Okay? It may be one of the most ugliest tools in the world, but it's amazingly powerful. It really is. Feeds of messages are stored together inside Kafka in a topic. Okay, so you would have a topic for logs, you would have a topic for metrics, and you would have a topic for application X, and you would group these messages together based on topics. Okay, systems that publish data to Kafka are called producers, and systems that read data from Kafka are called consumers. It's pretty simple. So Kafka topics are about as difficult as it gets. A Kafka topic is split over a number of partitions that you predefine. Okay, so 1, 2, 4, 8, 16, etc., etc. There's a whole partitioning idea behind it that you can go and read about, but just to keep it simple, we have like 3 partitions, okay? Each partition is an immutable, ordered sequence. Once it's been written, it cannot be changed. I promise you all these slides are all available afterwards. I'll just publish them on the hashtag, so don't worry about snapping or anything. Once it's been written to, it can't go back and be changed. So partition 1, index 0, cannot be changed. That is written, that is always there. That's not going to be available to change. And that partition 1, 0, is actually a unique identifier. Okay? Think of it as a git commit log, but not being able to rewrite history. Partitions are replicated over a number of servers that you tell it to, and that's for fault tolerance. And a partition has a server that acts as a leader, and the others in the cluster act as followers. Okay, and again, that's for failover, for redundancy. If the leader dies, then a follower will be promoted, and that will take over the leader position. Okay. If you have a Kafka cluster of 3 nodes, and you have 3 topics inside it, the leader of each topic will be different. Okay? It's not all through one server is the leader for all topics. It distributes the leader-follower mechanism across topics. That clear as mud. Excellent. So producers. Producers are responsible for where to publish the data. Okay, so let me put that in a better way. An application connects to your logging system, and it tells it, I need to write to the topic X. As soon as it connects, the leader will then understand topic X, and it will then push the data to the correct Kafka cluster in the correct topic. Okay? The producers have to tell Kafka where they're publishing the data. Kafka isn't clever enough to recognize a piece of JSON or a piece of text coming through and go, oh, I see inside that text that has this content. and therefore it goes to this topic. You have to tell Kafka where you want to log it or where you want to push that data. The producer is responsible then for choosing a partition in which to write to, and that can be done in a round-robin fashion. So if you go, think of it in goes partition 1, partition 2, partition 0, partition 1, partition 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, and it's like a little ticker, okay? It literally... Or you can then actually give it partition functions and say, I want X amount of data to be stored on this partition, Y amount to be stored in that, and Z amount to be stored in that, based on these specific criteria. So you can make it as easy or as complex as you want it. You can tell it was written by developers. They made it simple, and then they thought, let's add another layer of abstraction, because that's what we do good. I'm a developer, I can say that. And Kafka consumers have a number of different things, okay? So consumption can either be done in one of two ways, queuing or via pub/sub. Okay? In a queue, a pool of servers may read a message, and it goes to all servers in that queue. Okay? So if I have 3 servers that are connected to Kafka, and it's queuing, then all 3 servers will receive a copy of that message. Okay? In a pub/sub, the message is actually broadcast to all. So instead of the consumers connecting and reading, in a pub/sub, it's actually put out there, available for people to read when they want it. Standard pub/sub. Kafka consumers, Kafka has this idea of a consumer group that actually abstracts the notion of a pub/sub or queuing. It understands it for you, depending on how many people are connecting to it, and depending, has it gone really dark or is it just my eyes? That was weird. So it creates that layer of abstraction for you, and it will work out, based on the number of people actually connecting and reading data, is it a queue or is it a pub/sub? Consumers label themselves as a consumer group, and each message published in a topic is delivered to the consumer within the group. Okay, and you'll see a little bit more about this in a second. Okay, if all of the consumer instances have the same group, then it load balances. Okay, it works out all the different routes through. It's actually quite clever. And then lastly, it has strong ordering guarantees. This, for me, was the big pull of Kafka over something like AMQP or RabbitMQ or any of the other traditional messaging systems. Okay. Because each message in each partition has a unique ID, a unique identifier, and it's written to a partition, when a consumer connects and reads it back, it is guaranteed to be delivered in the order in which it was written. Thus, I was saying about a commit log, okay? Because when you do a git checkout or a git clone, it takes it in exactly the same way. It knows the change sets going through, and Kafka knows exactly the same thing. Okay. Lots of people are starting to now get into the event sourcing side of Kafka, and like event sourcing is not a new thing in development terms, but for this actual message system, it's pretty new, and people are starting to see, because it is strongly ordered, that it can get into that event side of things. I said that we use Zookeeper. Zookeeper, we had backed by Exhibitor. Anyone use Exhibitor? It's by Netflix. If you don't know Exhibitor, it's awesome. It will manage your Zookeeper process for you, and it will tell you all the Zookeeper nodes in the cluster, and it will allow you to restart them, and it'll allow you to see their logs and all their offsets and all the data held within. Okay? If you run Zookeeper, I strongly recommend you go and look at Exhibitor. Massive props to Netflix for giving that open source project. It's amazing. So we took all of these learnings from Kafka, and we put them into our messaging system, okay, or into our logging system. And we created a structure that looked like this. Again, we had our central data center, our main data center, and the application servers, again, wrote to the log processor nodes. Ignore the mirror maker bit. I'll talk about that in a second. And the log processor nodes push data into Kafka. Okay? Data was read out of Kafka and then brought into the Elasticsearch cluster at the bottom. And we had to mirror this exact same structure in each of our data centers. We needed to have everything the same. And then we came up against, how do we get data from a Kafka cluster in one data center and push it into Kafka in another data center? And Kafka has this process that's inside it called the mirror maker, where it will allow you to subscribe to Kafka data in one cluster and publish data to another cluster. So it is both a subscriber and a producer, okay, which worked perfectly for what we were trying to do. And all of the systems were allowed to talk through. So inside the log processor, we changed how things work. Okay, and this is how we actually got around the problems that we had with Redis before. So Redis no longer became our queuing mechanism. Okay? We wanted data to be in Redis as low a time as possible. We wanted it to arrive and be straight out. Okay? So what we actually did is we reversed the polarity. Before, Logstash would write to Redis, but now Redis was actually used as an input queue for Logstash, which would then take the data and pass it on to something else. We still used Redis because we had like 25 applications that had a logging library that was actually writing to Redis, and we didn't want to change anything for the developers. That wasn't fair. Our shortcomings shouldn't affect them having to do more work. So we kept Redis in place so that their applications could continue to work, and on the proviso that later, we would change the login infrastructure, or they would change their login libraries and write directly to Logstash or directly to Kafka or whatever. One thing to note, as we were in the .NET world, the client that writes to Kafka from .NET is really bad. Really bad. The Java world, you guys have a great client that connects, so you don't need to do that step. You can connect directly to Kafka. Much better. We still pushed all of our data through Logstash because Logstash gave us the ability to add types and add filters and change the state of messages. Okay, Logstash gives you that ability. You basically add filters on the front and say, when a message comes in of this type, add specific tags so that you can do things, so that you can actually allow to search inside Elasticsearch. So we still wanted as much data to go through Logstash as possible. This was probably an optimum solution. Okay, we ran all of our infrastructure, our login infrastructure in AWS. And at this point, the entire Elasticsearch cluster was about 90 M3 nodes, M3 large nodes, okay, which is approximately 744 gig of RAM. Okay. One thing we found is that Elasticsearch is very hungry for RAM. Very hungry for RAM. And we were getting up at this point to being able to write something in the region of 150, 200 million messages a day. We thought that was okay. We didn't realize is that there was actually only about 25% or 30% of our entire applications writing to this infrastructure. So then we had to go through another period of scaling. Okay. And of course, as we were developers, we created improvements. We added in more layers of abstraction because that's what we do well. And we created a system that looked like this. Notice what we did is in our main data center, we just implemented another layer of Kafka. So we had, in our secondary data center, we had Kafka talking into a main data center of Kafka, which then talked within the main data center of Kafka to Kafka. It was Kafka overload. It's crazy. I can see people going, what did they even do? Exactly, exactly. Now, the ideas were sound, okay? And I'll tell you what the ideas were. The secondary data center layout was perfect, okay? Each secondary data center had its own Kafka cluster. Perfect. But things became a little bit more difficult if we go back to this. things became a little bit more difficult in the main data center because our main Kafka cluster was also being treated as an application Kafka cluster. Does that make sense? So we were writing data from our secondary data centers into a cluster. It was being tagged and it had messages in a specific way, and then those messages would make their way into a central cluster. Because we still had application servers in our main database, they were going through a different level of logging. Okay? They would directly log processes, which would go directly into the central Kafka rather than via a mirror maker process. And we found that we wanted to make some changes. As we were having the scale up of our infrastructure, we needed to change how Kafka worked. We needed to change the sizing of instances, etc. So we thought, let's have each application server set talk to what we call feeder Kafkas. And then feeder Kafkas would be used in order to push data into the central Kafka instance. Okay. We had to change things a lot here. There was a number of things going on. Firstly, our Kafka clusters were M1 extra larges, okay, and each cluster was 3. So we had about, an M1 XL has 1.6 terabyte of instant storage available inside AWS, and we had 3 of those. Okay, so we had about 4 and a bit terabyte of data available, okay, and that was before we added any extra EBS volumes. But because of replication factors, we approximately had about 2.5 terabyte of storage on each Kafka cluster. And because Kafka uses disk, if you need to increase the storage, you just add more volumes, more drive space, and it will continue growing and growing and growing. Elasticsearch had scaled up huge. So we had 90 M3 nodes, which was 744 gigabyte of RAM, to 30 R32XLs. Okay, so we went from 744 gig of RAM to 1.8 terabyte of RAM. Because the usage had grown so much, we had to change all the servers under the hood. We needed to add more drive space, we needed to add more RAM, we needed to add bigger servers. And luckily, because we used the configuration management solution, we could do that. We could change things on the fly, and we could add new things in bits and pieces. One of the other reasons we split between a feeder Kafka and a central Kafka was that we thought that each feeder Kafka should store more data on them than the central Kafka. Because if there was a problem between any of our secondary data centers, and logs could not be read from the secondary data center and pushed into the central data center, that we should have longer amounts of data stored, and that in the central data center, because it was going through Kafka pretty fast and into Elasticsearch, that there would be a shorter retention policy there. So that was another one of the reasons why we split things out. And the numbers were as follows, okay? We kept logs in Elasticsearch for about 30 days. We always had 30 days worth of data searchable. Okay? That created about 12 billion documents. And our space used in Elasticsearch was between 25 to 30 terabyte. Okay, so it was pretty big. It wasn't like huge. It wasn't what you call big data. It was just a decent size of data that nobody used. Now, I take that back. People had dashboards for 7 days. Lots of people only really wanted to see 7 days worth of data, except those crazy data scientists guys, which were like, give me more data, give me more. And the average doc size was about 1.2 kilobyte, which seems quite large. Yeah. Some people were logging megabytes of JSON. Megabytes. Yeah. One team actually logged 50 megabytes of a JSON message. It wasn't their fault, to be honest. They had a recursive log in place, which the log was then logging the stack trace of the stack trace of the stack trace of the stack trace of the .NET CLR. I'm okay. If we didn't have this solution in place, they wouldn't have known that their application was doing that. So we can tolerate that. They did DDoS our entire server, but that's all right. That's not a problem. And We found that on average it was about 1.2 kilobytes, okay, which was a reasonable size. And the CTO had given us the message of our logging infrastructure needs to be scalable and elastic to stand up to the main time of the year. Okay, the main time, there's 3 main times a year for OpenTable. Okay, New Year's Eve, Valentine's Day, and Mother's Day. Mother's Day in the US. Okay, I don't know when Mother's Day is in Germany, but we have a different day than the US, and probably you guys have a different day from us. So Mother's Day for the US, it's really important. And we found that traffic ramped up across the course of the week coming up to Mother's Day and Valentine's Day and New Year's Eve, and then you would have a huge spike the day before because everyone forgets about their mothers and their wives and their boyfriends, etc. And we needed to be in that situation. There was a time when we hated, as an operations team, we hated those times of year because our system would fall over all the time. On Valentine's Day just passed, we collected about 750 million documents without any failure. No idea how many documents was tried to be pushed into the system. That's a different problem. The system was able to process 750 million documents, and I didn't get a single page, which was awesome. One thing about this as well, a lot of teams were logging via HTTP. So I mentioned about somebody DDoSing us because of the size of message. Yeah, they did that a lot as well because of HTTP. When the application servers went down or Logstash went down, and the applications were actually trying to connect to our system, they would continually connect and try and reconnect, and try and reconnect, and try and reconnect. So we had lots of systems bombarding us and actually pulling down our own logging infrastructure. So don't log via HTTP. It's a bad idea. We needed a huge amount of metrics and monitoring on our own logging solution. This is like inception time. Logging of logging. Okay, and we used a number of tools. Nagios? Anyone use Nagios? Yay. Anyone use Sensu? Ooh, that's a new kid on the block. Anyone use iChinga? It's actually a German-based tool. Yay. And we had alerts with Nagios based on our Elasticsearch cluster, Zookeeper and Kafka nodes, Logstash and Redis nodes, etc., etc. And all of these checks are all open source that we wrote, okay? So we used Puppet. So we used Puppet exported resources, which means every time a new server was added, it would export its own resources to Nagios, and Nagios would just grow and grow and grow. And we had checks on the Logstash service, Redis service, whether Elasticsearch was in split brain. We checked the number of nodes in Elasticsearch. There's a whole plethora of Elasticsearch checks in my GitHub repository. If you want them, feel free to take them. So we think we knew when our server was working, or at least when our servers were up. Okay. We also had metrics around the Kafka offsets. So an offset is when there's data in a topic and there's a consumer that's subscribing to it in the pub/sub manner, the offset is the number behind real time. Okay, because in a pub/sub, as a message is put out, they should read it instantly. Because it's a pub/sub, it subscribes to it instantly. And the offset is that number that they were behind. So we needed metrics on that because we needed to see when the mirror makers couldn't read data from our secondary Kafkas into our main data center. And the offset monitor helped that. And we were able to create some graphs that looked like that. So we could see this green one right up there? That should actually be level. There shouldn't be a lag. But by putting this graph in place, we could see that we were a couple of thousand behind at all times. A couple of thousand is nothing. When we had a network failure, we got to 25 to 40 million behind. And that was like within an hour. So it was important to put some metrics in place. And there is an open source project called the Kafka Offset Monitor. OpenTable forked it, and I've got a pull request waiting to be merged. And the reason we forked it is that we wanted to push all of that data back into Graphite. Graphite's a time series database so that we could actually graph it and see it, rather than having a third-party application that we would have to monitor. We also needed metrics on Elasticsearch. Elasticsearch was a bit of a beast. That's the only way I can describe it. All you people that work in Java, you guys are lucky, okay? Because as you've developed your career, you've begun to understand the JVM, okay? The JVM for us people outside of Java is like a black box. It's wizardry. We have no idea what's going on in there. And of course, Elasticsearch is based on top of the JVM. And we had no clue what was happening. So we had all sorts of graphs. First thing we wanted to do was we needed to graph things like document count, okay, indexes, amount of RAM used, amount of CPU used, amount of disk space used. And we could see this was actually on the week upcoming to Valentine's Day. You can see that growth. That growth is from about 9 billion documents to about 12 billion documents. Okay? And that's in like 3 billion extra documents in a week. And previously, before we had this scalable solution in place, it just used to crash and we would have no clue what was happening. So we needed to put these metrics in place and we needed to use JMX in order to pull a lot of these stats out. And actually, we wanted to plot them. It allowed us to create graphs that looked like this, really pretty. We have no idea what they are. I'm kidding. It's like heap usage, and it's like JVM, flush rate, etc. So we could see exactly what was going on. I had no idea what it was doing, but I could see that we could spot trends and say, oh, we've just had a big cache filter dump. That usually means it's because the JVM is just about to crash on us because we've just... But, you know, too much data has gone through one of our nodes and it's not tuned enough. So we could see that there was a correlation between when there was, I don't know if you can see the graph above, we had an area in the middle that just sort of disappeared. And that was just because the JVM crashed on us. So we could start to see, and we had other graphs that did other things. And here was one of those heap usage dumps. So we would get to about 1.4 gig of heap, and then it would just completely crash on us and dump, and we could start to see. So we had more of an understanding of what it was. Still .NET developers. Still don't know what it's really doing. But visibility rocks. Okay. You can't run a project like this unless you have very visible statistics, very visible metrics, because it's called situational awareness. Situational awareness is when you understand what is happening around you. When you don't have situational awareness as an operations team, you cannot understand what is going on. The most embarrassing thing for a member of ops is when a developer tells you your system is down. That really sucks. Because usually it's the other way around. We tell you when your system sucks. I'm kidding, we don't. This whole thing, this area of visibility gave us, we were starting to build a culture of everyone understanding and having all of the systems in place that they could see what was happening in production. Our definition of done went from something being released to something being released and monitored and feedback mechanisms being available. And we could build dashboards that looked like this. Okay. This was one of the team's actual dashboards. And when application logs were read in and Logstash mutated the tags, this was because they wanted to build these types of dashboards. So in the top left, that was total number of requests. Okay. Top middle is the number of non-200s. And top right is the number of deployments. Okay, that's a vanity metric. I never really liked that one. But deployments were used for other reasons. Here and here, and there was ones further down. There are little tags, okay? Those tags are when the deployments occurred. And we could see that when a deployment occurred, if it increased the performance or the CPU or the RAM, or if it had, these guys were talking to Redis, an application that was talking to a different Redis cluster. We could see if different amounts of cache rate misses was happening. And we could quickly give them the tools to turn around and say, that's a very bad release. That's degraded the performance of the system by 10%. Let's quickly put a fix in place and change it. So when you have a central system that allows you to do this type of thing. Anyone use central login systems? Who's going to go back on Monday and start implementing one? Nobody. Ugh. And from this, they could start to understand what was happening in production. This was one of the key areas of what we were trying to achieve. We didn't want the teams, because we were trying to re-architect our system from a huge monolithic ASP.NET application into a microservice and microsite-based system, and we had all services talking to other services in a huge spider web. We didn't want blame to creep into the culture. We didn't want this team to turn around and tell somebody whose applications they were consuming, your applications suck because your increased rate. We wanted them to see it first. Okay? They needed to actually take responsibility for their own system. So what would I do differently? Firstly, I would not have implemented that third layer of Kafka. That was like the worst mistake ever. It was just, I gave this talk in Sweden last week, and somebody asked me, they went, how big was your cluster at this point? It was about 156 nodes. Okay? That's a decent amount of infrastructure for a team that was stretched already pretty thinly, an ops team that was stretched quite thinly to manage extra. Okay? It cost about $12,000 a month to run, on average. Some months it could be scaled more, other months it could be scaled down. January was a very quiet month, for example. But on average, across the course of the year, it was about $12,000. And one of the other big areas is that we couldn't actually offer any guarantees to the developers that if they actually wrote 50 messages, that 50 messages came out the other side. What's 50 messages between friends? But the point is that I would have put more metrics in place. Okay, metrics are fantastic. Metrics, as I say, metrics help you understand your system. Okay? Has anyone read the Jepson series of database bashing? Okay, there's a guy on Twitter called Kyle Kingsbury, and you should check him out. And he's basically taken every database that's out there in turn and torn it apart. Okay, because we believe that when we use a database and we write to a database, that it gets stored. Okay, he's actually proved that there is different percentages. There's different databases that lose data in different percentage of ways. Okay, I'm not going to name any names, but MongoDB is one of the worst. He's actually working really closely with MongoDB now in order to actually help them, show them the areas, and this is the point of the project. And one of the last presenters asked me, he was like, you know, could you guarantee that data got into Kafka? We couldn't. Because we didn't have the metrics in place in order to say 50 messages read in, 50 messages came out the other side. But 750 million messages in a day is about 8,000 messages a second. 6,500 messages a second, something like that. Okay? So having those types of metrics going through the system, as this was central login, we could be okay with losing a percentage of data. Okay, as usage stats were going in, if we were billing clients for how many requests they were using, this probably wasn't the sensible idea for that type of thing. You would have to put extra visibility in place and extra measurements in place in order to guarantee that that was the case. But we needed to be in a situation where we could take more than 15 million messages in a day. Right? 15 million, 750 million. It's a huge amount. It's a huge jump. It's like 30 times more. 50 times more. 50 times more. So definitely we would need to understand the metrics read in versus metrics read out. I would not choose M3 large nodes for Elasticsearch. Elasticsearch, as I said, is extremely, extremely hungry. I would choose actual instance optimized, RAM optimized nodes from the offset. Okay, we thought that we were trying to save money, But when we were growing 5 and 10 extra nodes a day at one point, we were like, we've got to change this. We have to change this. And I would happily have sent out tweets when this was scaling and go, oh, just added 5 more nodes to my Elasticsearch cluster. Everyone was like, how big is your Elasticsearch cluster? And I was like, 90 nodes. And they're like, maybe you should look at your instance sizing. 90 nodes seems a lot for what you're trying to do with it. And it was because we chose the wrong sizes. I would choose probably I series in AWS going forward rather than R3 or M. I would so much have liked to have understood the JVM more. So if anyone has like a spare 4.5 or 6 weeks in order to try and coach me in the JVM, then I will pay for that service. I really will. Now, in actual seriousness, the power of this solution was so much that I would often sit and scratch my head and go, huh? Just because it was able to process so much data in such a quick amount of time that we were just blown away by it. We really were. It was fantastic. And the tools that were in place, like Logstash, amazing, and they've worked on performance and startup times. Elasticsearch is just incredible. It's a free text-based system based on top of Lucene. And when it's able to process billions of documents, that is just amazing. And then Kafka being able to be used as a storage mechanism. All of these things just plugged so well together to make the system that we were trying to achieve. So I would definitely need to understand the JVM more. I would have dedicated a whole team to logging infrastructure. Logging is, I'm very much a person who believes that everybody should have interaction with everyone, okay? If you want to go and write some config management code, and you have full access to my database in order to send, or my source code in order to send me a pull request for that, okay? When it came to this solution, because we were already stretched quite thinly as an ops team, I would actually have nearly have created an ops team that looked after logging. I definitely wouldn't have used Redis as the queuing mechanism, to be totally honest with you. And people who use Redis as your queuing mechanism, you probably will have problems at some point. And Redis can be really well tuned in order to mitigate a lot of those problems, but unless you're running in a clustered mode, single databases are bad. Very bad. So there were a number of areas in which we wanted to change. Does anybody have any questions so far? Wow, tough crowd. Who's awake? There's a couple of people awake. There's a whole area of code around this, okay? And if I'm still connected to the internet. Yep. Puppet exhibitor is there. Puppet Kafka is there. These are all open source projects. Okay? I'm not signed into I'm signed out of GitHub, but they're all public projects. Okay? All this code is out there. You do not have to rebuild all of this yourself. Go and use the tools that other people have created, and you can have your Jenkins set up on your CD pipeline, like from the last talk, in order to build your system. But all of the code is out there. So you can take it, you can experiment it. There's a lot of vagrant environments that you can just download, and you can just run a single Kafka, single Logstash, or single Zookeeper system, and that you can actually start to write write and subscribe to in order to see what it's doing. But everything is open source, and it's really important that our CTO told us at the time, he said, you can spend as much money as you want on this. Okay, we will let you buy Splunk. Okay? It probably would have been a really good investment if we bought Splunk from the start, because we wouldn't have gone through a year and a half of pain and $12,000 a month. But we have now, before I left the company, we had developed a system that could scale as the new applications and new architecture can scale, which is part of what we do, okay? We're software developers. We like to develop systems. A big bang system probably would have helped us at the outset, but we wouldn't have been able to grow it in the way that we wanted to grow it. So a third-party system wasn't really what I wanted to use. So if there's no questions, oh.
You use Logstash, and we also try to use Logstash, and the biggest problem we have with this is people cite its huge RAM consumption, that it's likely to do not exactly what you want and then crashes.
Okay, so the question is that why do we use Logstash when other people have...
Did you use it, and how did you avoid this problem? Or did you lose messages because of that? Or did you not encounter this problem at all, and it's likely to...
Okay, so the question is that did we encounter any problems with Logstash, and was that part of the reason why we lost messages? Yes. So we used Logstash as a forwarder, okay? We did not want data to be sitting on servers anywhere apart from Kafka. Kafka needed to be the message store. So Logstash for us was the transport mechanism, okay? Now, because Logstash was being used in two ways. One, it was being used as a forwarder for applications that were logging directly to it. And two, it was being used to read data from Redis. We could see that when Logstash wasn't working and it crashed, Redis still continually ticked up. So we had good visibility around when Logstash service had crashed and when it hadn't. Now, in Logstash 1.5, which was released very, very recently, their performance tuning has gone through the roof. They've worked a hell of an amount of trying to make it better and to try and stop having those problems. But there are, as any third-party tool, there are some internals that we just couldn't see and we just couldn't work out. So it may have encountered for some of the message loss. I think, personally speaking, for us, a lot of the message loss was between data centers when there was network partitions. So, and when you're reading data from EU West, so Ireland, and it's going to our main data center, which was in California, or Oregon, excuse me, there was always going to be problems when we were pushing data that way around. So we would have probably designed it to be a little bit better and used a different mechanism in order to transport the data across. Make sense?
Okay. And another thing is, why didn't you use, when it's only before, what are something more basic and a bit fast and reliable like syslog?
Because .NET. Yeah, we talked about that, and we talked about, so the question is, why didn't we use something more reliable for forwarding like syslog, okay? Windows sucks. It's not really, I'm just kidding. Windows is getting better, it really is, but we didn't have those types of systems available to us in the Windows world, okay? Now, granted, logging via HTTP was probably a terrible idea, and there's lots of people sitting there going, yes, it is, yes. And it is, but what we would have done and what we had planned to do was we were going to log to local disk and have a process from our Windows boxes called nxlog, and that would have picked up the messages and forwarded them through in the same way as syslog, okay? That didn't work for Windows 2003. And that's the troubles. We had some systems that were still very, very legacy and hadn't been worked on in a very long time, and other systems were much better, and the developers were learning not to deploy them on Windows. So. Any others?
Can you talk a little bit more about the RabbitMQ compared with the Kafka solution? So what makes you choose Kafka in the first place?
Erlang. Setting up RabbitMQ in a clustered way is really tough. It's really, really tough. But we didn't know if we could utilize the throughput of RabbitMQ in the same way that we could for Kafka. Okay? So we were standing on the shoulders of LinkedIn here. Okay? LinkedIn take hundreds of billions of messages a day through their Kafka cluster and are very good at it. And they were the 16 floors above us in our office in San Francisco. So if anything went wrong, we could go and ask them. But there was lots of use cases out there that was showing that Kafka was really good for this types of system. Okay? We needed it to be strongly ordered because we needed the messages to come out in a reasonable order that, you know, a request came in at midday and a request came in at 12:01 and a request came in at 12:02. We didn't want the request at 12:02 to be read out first because then there would be a 2-minute delay on some messages and compared to others. So we wanted them to come out in a specific order. And Rabbit is in that, it's not a strongly ordered system. So that was the reason why we didn't choose it.
Another thing I heard yesterday in the talk, there was also someone talking about logging, and they used RabbitMQ, and he said at some point when they get a decent amount of documents, RabbitMQ wasn't able even to keep it up because of something in the RabbitMQ. There is a kind of upper limit, and it just denied to work then above this limit. And
as a good developer there, we would have had RabbitMQ talking to RabbitMQ, which then talked to RabbitMQ and talked to RabbitMQ. We would have had like chain RabbitMQs, because that's what we do. But no, this wasn't a case of RabbitMQ was bad. This was just a case of Kafka fitted the type of model that we were trying to build. And because it stored everything on disk, if we needed to grow, we just needed to add more disk. Disk is cheap. Disk is really cheap in comparison to RAM. So that's why we chose that over Rabbit.
Would it be feasible to use Cassandra instead of Kafka?
Yay, Cassandra. Yes. Yes, it would. So we actually, I didn't want to talk about this too much, but you've just segued in, and I have 1 minute 44 seconds. But I said we kept 30 days active data in Elasticsearch. Okay? Every day that went through it, Kafka, because it was going to that central Kafka, Elasticsearch just became a consumer of that Kafka. Cassandra also became a consumer of that Kafka in order for the data sciences guys. And they had a huge Cassandra database that they were actually able to write queries against for their data sciences needs. And that's exactly what they used, Cassandra, for that. So that was, we could have stored all the data in Cassandra rather than Kafka, but because of the event source and the pub sub nature of Kafka, if they tore down their Cassandra database, they could just rebuild it from the source and then just say, give me the last 20 days, 30 days, 40 days, and it would be read out in the order in which it was written into Kafka. So it allowed them to do whatever they want and allowed them to really change, mutate, destroy the data, and then refill it from source. So, any last questions? Awesome. Thank you all very much. Please get in contact if you have any questions or want to see some sample code. I have sample code with me if anybody's interested, and enjoy the rest of your day. Thank you.